Welcome back, everyone. So Camille will tell us about will continue telling us about measure equivalence and negative curvature.
Thank you. Okay, so my goal today is to prove Adam's theorem that I stated at the end of my lecture yesterday. That gives obstruction on groups that are measure equivalent to a hyperbolic group. So let me give the statement again. So you have G, a non-elementary hyperbolic group, meaning infinite and not virtually Z. H is any countable group. And let's assume that H contains an infinite amenable subgroup with non-amenable normalizer. Then H cannot be measure equivalent. Okay, so if a countable group is measure equivalent to a hyperbolic group, then the normalizer of every infinite amenable subgroup must itself be amenable. In particular, the centralizer of every infinite order element must be amenable. In particular, G cannot be measure equivalent to product of two infinite groups. Okay, so the goal of the lecture is to prove this, and I will start as a warm-up by doing something that by itself may look a bit stupid, but it's really going to help us for later. So I'm first going to give you a proof that H cannot be isomorphic to G. So of course, we know that H cannot be isomorphic to G because we know things about hyperbolic groups. But the point of this is that I will write the proof in a way that, so later, instead of proving that they're not isomorphic, we will have to prove that they cannot generate the same orbit equivalence relation. And I will write a proof that completely translates to the setting of orbit equivalence relations. And the thing, so I first do the proof in the group setting so that it's kind of simpler to grasp. And then in the rest of the lecture, I will explain you what are the tools that you need about equivalence relations to translate the proof in this measurable setting. Okay, so let's do this. So assume towards a contradiction that H is isomorphic to G. Okay, so I want to exploit my infinite amenable subgroup A. And the thing, for example, is I don't want to say that A has to be infinite cyclic, right? Because being infinite cyclic is not something that's invariant under measure equivalence. I just want to exploit amenability. So how will I exploit amenability of A? Well, one way to do this is, so we know that G acts by homeomorphism on its Gromov boundary, which is compact and metrizable. And therefore, since A is amenable, well, we know that whenever, so A is a subgroup of H, but through the isomorphism, I view it as a subgroup of G. And so you know that whenever an amenable group acts on a compact metrizable space, you have an invariant probability measure, right? So I use amenability to find some A invariant probability measure on the Gromov boundary. And typically later, so I will have an amenable sub-equivalence relation, and I will use this to find some invariant probability measure in some sense that I will explain. Okay, now there are two cases. The first case, so I'm going to analyze this probability measure, and the first case is that the support of this measure has cardinality at least 3. Right? So you have the boundary. There are at least 3 points in the support. Now, if the measure has support at least 3, this implies that if I look at nu tensor nu, which is a probability measure on the boundary to the cubed, then this gives positive measure to the subspace made of pairwise distinct triples. Okay. So up to renormalizing, so I have so this is a probability measure on this space. It gives positive measure to that space. So if I renormalize, I can assume that I have a probability measure on that space. That's invariant. So up to renormalizing, I get an A invariant probability measure on the space of pairwise distinct triples. Now, the important thing that I will use is that in a hyperbolic group, whenever you have 3 distinct points in the boundary, you can take a barycenter, meaning that I can join those by quasi-geodesic, and there is some center here, which is a bounded region. Because it's a bounded region in the Cayley graph of G, which is locally finite, it's actually a finite subset of G. Right? So if you are in a tree, when you have 3 points in the boundary, you can really find one center. In a hyperbolic group, you can find a finite set that's invariant. So the fact is, the geometric fact that is really key in Adam's proof is that there exists a G equivariant barycenter map from the space of triples to finite subsets of G. So this is my notation for non-empty finite subsets. Okay, and if I push forward nu twiddle through the barycenter map, I get an A invariant probability measure on this set. Finite subsets of G. Now, the set of finite subsets of G is countable. Okay, so if I have a probability measure on a countable set, it's atomic. And therefore, it's atomic, and you can look at the elements that have the maximal measure, and there will be finitely many of them. Because I guess, right, it's delta, right? The size is delta. Yeah, right. So here I could do like at most delta. Yeah. But sure. I think I only need finite, but sure. Yeah. Okay, so I was saying, since this is countable, whenever you have, yes.
What's the problem with, say, something like assigning a ball from
Yeah, this is fine. This is fine. Well, you need the construction to be equivariant. I mean, in a tree, it's clear what to do. In a hyperbolic space, you have to be a bit more careful to have it. But this is basically it. Okay, so now the thing I will do is, if I have a probability measure on this countable set, I just extract the finitely many elements of maximal measure. So it gives me finitely many finite sets, and I can take their unions. And so if I have an A invariant probability measure on this, I actually find an A invariant finite subset of G, this set, and this is a contradiction because the action of G on itself is free. Okay, and the second case is the other one where the support of nu is at most 2 elements. And in fact, not only can I assume that the support of nu is at most 2 elements, but I can assume that for any invariant probability measure on the boundary, the support has at most 2 elements. Otherwise, I take one that has support at least 3 and I run this off. So I can assume that for every A invariant probability measure on the boundary, the support of nu has a cardinality at most 2. And so this means that, so you have some invariant probability measures. So this gives you either an invariant point at infinity or an invariant pair of points. But I'm claiming that there is a unique maximal A invariant subset of the boundary of cardinality at most 2. Non-empty subset of the boundary of cardinality at most 2, right? Because if you had 2 of them that are distinct, for example, those 2, well, then the uniform probability measure on those 4 points would be an A invariant probability measure with support at least 3. So you have a unique maximal A invariant thing. So it could be that, so you could have the first, which is 1 point, the second, which is a second point, and then the maximal A invariant is the union of the 2, but you cannot do more. Okay, and finally, I use the normality of A in its normalizer to say that, so of course, an A invariant subset is sent by the normalizer to another A invariant subset. So because you have one which is canonical, this subset is invariant under the normalizer. And this is a contradiction to the fact that point stabilizers in the boundary are known to be amenable. Whereas I assume that the normalizer of A in H and therefore in G through the isomorphism was non-amenable. Okay. So what did I use in this proof? So there are two things that I will need to translate to the measurable setting. One is what does it mean that an amenable subrelation gives some sort of invariant probability measure? And the other thing I need to explain is something about, there is a notion of one subrelation being normalized by another. So there is a notion of having this amenable subrelation with non-amenable normalizer. And so this I will explain you. And notice that we use two important geometric ingredients. One is the existence of this barycenter map, which is a crucial feature of negative curvature. And the other is here the amenability of point stabilizers. In fact, in the measurable setting, we will need something a bit stronger than amenability of the point stabilizers. We will need something that is called the amenability of the action of G on its boundary. Right? So this amenability of point stabilizers will have to be replaced, and I will explain right now what this means by Borel amenability of the action of G on its boundary. Okay, do you have any questions so far? So basically the plan now is we have this proof, which, okay, we've proved something that we already knew, but now I will try to explain you how to translate the proof to the measurable setting to get atoms. Yes. Yes, right. So, okay, let's imagine that you find one of cardinality 2. I say there cannot be another one of cardinality 2 that's distinct, because otherwise the union of the two would be an A invariant set of cardinality 3 or 4. And if you take the uniform probability measure, you would get it. So this is why I'm assuming that for every measure. Any other questions? Okay, so let me tell you what we need as a replacement for this. So G is always a countable group. Let me write it. G, the countable group. And let Z be, let's say, a standard Borel space equipped with the G action by Borel automorphisms. So we say that the G action on Z, so Z for us will be the boundary, is Borel amenable if the following holds. So I need a sequence of maps, mu n, where to every point in the set, I will associate a probability measure on the group. Those should be measurable when this is equipped with the weak star topology. Or, I mean, here, no, it's just a countable group, so pointwise topology of pointwise convergence. So to every point in the space, I associate a sequence of probability measures on the group in a way that is asymptotically equivariant. So I want that for every element in the group and every point in Z. So there are two measures that I can consider. Either I consider the measure nu n evaluated at the point Gx, or I consider the measure evaluated at the point X and translated by G. Right? So translated by G here this means, so the G translate of nu n of x is the measure that, so if you evaluate it on an element h of G, you get nu n of x evaluated at G inverse of h. Right, so those are two measures I can form, nu n evaluated at Gx or nu n evaluated at x and translated by G. I want those to be close in the sense that the L1 norm of the difference should converge to 0. Yes. Yes. So sequence of measurable maps, a way of assigning to every point a sequence of probability measures on the group that is asymptotically equivariant. Notice that, so one equivalent definition of amenability is requiring that there exists a sequence of probability measures on the group itself that is asymptotically invariant, right? So this would mean a sequence of probability measures on the group that do not depend on any space Z. In other words, what I'm saying is that right, so the first example is that G is amenable if and only if the G action on a point is Borel amenable. This is saying that there is a sequence of probability measures on the group that's asymptotically invariant and with no reference to any point x. But the interest of this notion is that there are many non-amenable groups that have amenable actions, and maybe the first example is the free group acting on its boundary is a Borel amenable action. So let me prove this. We have the free group acting on its scaling graph, and what I need to do is to every point C, let's say this is the origin, maybe the identity of the group. To every point C in the boundary, I need to associate a probability measure nu n of C, a sequence of probability measures nu n of C. How do I do this? Well, so I have my fixed origin identity of the group in the Cayley graph, say, and I can look at the unique ray from identity to C. And what I will do is I will look at the first n elements, so those vertices correspond to elements of the group that I encounter along the ray, right? So nu n of C, and I take the uniform probability measure of this. So nu n of C is the uniform probability measure on, so I take the ray from identity to C, and I only remember the first n vertices that I need. So this is the set of the n first elements along the ray from identity to C. Okay, why is this equivariant? So I need to, why is it asymptotically equivariant? So I need to compare nu n of C with, let's say, G inverse of nu n of GC. So this measure, we know what this is. So what is that measure? So if you look at nu n of GC, it's the uniform probability measure on the first endpoint that you see from identity to GC. If I translate by G inverse, I will find the uniform probability measure on the first n vertices from G inverse to C. Right, so this is the uniform probability on the first n points on the ray from the element G inverse in the group to the boundary point C. But now you see that those two rays, they only differ by a finite initial amount. So as you let n go to infinity, those two sets, we have more and more vertices in common. And so when you take the uniform probability measure, the difference in L1 norm will go to 0 as required. So really the important geometric feature that makes this proof work is that any two rays that target the same point at infinity eventually coincide. And this again is a feature that you often find in negative curvature. And so building on this idea, Adams proved that if G is a hyperbolic group, then the action of G on its Gromov boundary is Borel amenable. Now, of course, this is much more technical than this case because the two rays do not coincide on the nose, but you have some bounded error to take into account. But this is the global intuition behind the theorem. And I should say that this kind of statement has been proved in many other settings. For example, Ozawa proved that the action of variation for relatively hyperbolic groups acting on the part at infinity of the Bowditch boundary. Or so there is so you have things for groups acting on locally finite cat-zero cube complexes acting on their roller boundary. Lecurup proved something for groups acting on locally finite buildings. The action on a suitable compactification of the building is Borel amenable. Hida proved that the action of a mapping class group on the boundary of its curve graph is Borel amenable. Also in the out Fn setting with Besvina and Girardel, we proved that the action of out Fn on the boundary of, for example, a free factor complex is Borel amenable. So you have many settings where you can use this kind of idea of negative curvature to prove Borel amenability of certain actions at infinity. So, right, so I can relate Borel amenability to Zimmer amenability. So what is true is that when the action is Borel amenable, this implies that it's Zimmer amenable with respect to any quasi-invariant measure. Yeah. The other way is I don't like, okay, so only just, yes. 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 Yeah. Right. Yes. Well, I guess I'm not sure it's equivalent. I think so. Borel amenability and universal amenability. Like, of course, if you just fix one measure, Borel amenability is not equivalent to Zimmer amenability for one measure, but you can ask him for every measure. And this, I'm not sure. I know one implication is not true. Okay, maybe also a little observation is that also, of course, the action of G on subsets of cardinality at most two is also Borel amenable, because if you have a pair of points, you can just take the average of the two measures. This will give you the map. Okay, so let's now go back to the measure equivalent setting. Maybe for simplicity, just for kind of notational simplicity, let me prove that, so in the setting of Adams' theorem, let me prove that H is not orbit equivalent to G. I mean, it's exactly the same proof for measure equivalent, but just for simplicity of notation. So let's assume towards a contradiction that those two are orbit equivalent. And as we saw yesterday, this means that I can find two free ergodic probability measure preserving actions of G and H on some standard probability space X that have the same orbit. And I will denote by R the common orbit equivalence relation. So the equivalence relation on X where 2 points are equivalent if and only if they are in the same G or equivalently H orbit. Because this is always well defined up to a null set where they have the same orbit up to measure 0. Anyway. And notice that this equivalence relation is equipped with two cocycles. One from R to G, where to a pair XY in the relation, you associate the unique element of G that sends X to Y. And another from R to H, where you associate the unique element of H that sends X to Y for the H action. Okay, so this will be our setting. And now, so I want to run the proof that I presented at the beginning. And the first step was to take some amenable subgroup and find an invariant probability measure. So I need to tell you about amenable sub-equivalence relation. In the sense of Zimmer, so that this is what we were alluding to. And maybe, so we saw a characterization of amenable sub-equivalence relations yesterday, which is they are characterized by being hyperfinite. But this is a deep theorem of Cohn, Feldman, and Weiss, and it's not Zimmer's original definition, of course. Maybe before I give you the actual definition of Zimmer amenability, which I actually won't really use, let me rather highlight some important facts about amenable relations, which are things that you would expect from an amenable equivalence relation, and which are the facts that I will actually use in the proof. Okay, so the first thing is that so if A is an amenable subgroup of G, or same for an amenable subgroup of H, then you want, so if I look at rho G inverse of A, so what is rho G inverse of A? It's just like the sub-equivalence relation induced by the A action. So you're only looking at the A action of X and the sub-equivalence relation. So you want to say if you have an amenable group that's acting, the equivalence relation should be amenable. So this is true. The equivalence relation associated to an amenable subgroup is an amenable equivalence relation. And in fact, this is an if and only if. If you take a non-amenable subgroup of G, then the equivalence relation will be non-amenable. But we also want to exploit our amenable actions. And so there is something more general, which is if S is a sub-equivalence relation of R, if you have, so I write everything with G, but of course the same thing works if I replace G by H. If G acts as a Borel amenable action on a space Z, and if you can find an S, if you can find an equivariant map for the cocycle rho G from X to Z, then S is amenable. So this is an extension of this to not just amenable groups, but amenable actions. So what does it mean to have a rho equivariant map from X to Z? So this means that for X, you have the pair of points X, Y in the subrelation S. You want, let me call it F. You want F of Y to be rho G of XY F of X. Right? So what does this mean? So to every point X, I associate a point of Z. And I want this assignment to be equivariant in the sense that if I go from X to Y and it's the element G that brings me from X to Y, I should be applying G to, so if here I send X is sent to Z, then Y should be sent to G times Z. If it's G that's sending X to Y for the cocycle rho G. Okay, I think I should probably attribute this to Adams, Elliott, and Giordano. The idea is that in this setting, you can always view S. You can always realize S as obtained by letting G act on some bigger space than X hat, which will typically have infinite measure. So you have an action of G on X hat that quasi-preserves an possibly infinite measure, and you restrict to it. And the thing is, so you can realize S, a subrelation, as some restriction to a Borel subset of an equivalence relation that's associated to an action of G on some bigger space, X hat. And the thing is, if you have a map F from X to Z, you can actually extend it to a map from X hat to Z that's G equivariant. And what they say is that if you have two actions, G on X hat, G on Z, and if you know that the action of Z is amenable, then the action of X hat will be amenable. So X hat comes with a measure, Z is equipped with the push forward of the measure. The action of G on Z is amenable with respect to that measure, and therefore so is this. Well, anyway, this is something we need, which says, like, you can exploit Borel amenability of actions to prove the amenability of certain subgroupoids. right? So it's really an extension of this one, because so here, this has a cocycle to A. A is acting Borel amenable on a point, and you always have a map from X to a point. And so it tells you that this one is amenable. So this is a generalization in the presence of Borel amenable actions. The third thing that I will need is that, so if S is an amenable sub-equivalence relation of R, and if G acts on some compact metrizable space by homeomorphisms, then there exists an equivariant map from X to the space of probability measures on K equipped with the weak star topology. So this map is equivariant when probability measures on K is equipped with the weak star topology, which is the extension of the fact that an amenable group will have an invariant probability measure. So here you don't have an invariant probability, just one invariant probability measure, but you have above every point a probability measure, and they vary equivariantly with respect to your cocycle. Okay, so maybe I can give you the definition due to Zimmer of amenability of an equivalence relation. In terms of actions on convex sets. Right, so let's say an equivalence relation R is amenable in the sense of Zimmer if for every separable real Banach space. So it's a fixed point property for actions on Banach spaces for every separable real Banach space E. And whenever you have some cocycle from R to the group of isometries of E, if you have some invariant convex field over X, so meaning that you have an R, so rho star is G, a joint of rho. You have a rho star equivariant measurable map from X to the space of convex compact subsets of non-empty convex compact subsets of the unit ball of the dual of E. Right, so I have above every point, I have a convex set in the convex compact subset of the unit ball of the dual of E that varies in an equivariant way with respect to some cocycle. Then I can always find an equivariant section. So pick one point in the convex set equivariantly and in a measurable way. Okay. This probably looks quite technical if you have never seen this kind of things. But really, I will not use this definition. I will use the facts that I mentioned before. This is a consequence of the definition by choosing for E the space of continuous functions on X. And so, you know, the dual will, the unit ball of the dual will be identified with probability measures. And so this is a way of selecting a probability measure above every point. the fact that, yeah, right. So an invariant convex field, you can also view this as a compact convex subset in L infinity from X to E star or E1 star. And so if you have an amenable group, then you will find an invariant point in L infinity from X to E1 star, and this is an invariant section. This is why this justifies the first point. If you have an amenable group, then all of its actions are amenable. Okay, so I won't say more, but really the 3 points I highlighted are the ones that I will use later in the. You have any questions? Okay, so to every pair of points, you associate some element in the group, here in the group of isometries, and with the property that if you have two arrows that compose, then the position is just. Any other questions? Okay, so the next thing I need is the notion of normal subrelations. So we want to exploit that there is some amenable subrelation with non-amenable normalizer. So I need to tell you what it means for one subrelation to be normal or normalized by another. Okay. Okay. So first, let me say that the bisection of R so my equivalence relation, which I view as a subset of X cross X. So bisection is just a Borel subset such that the restriction of the two projections the two projection maps to B are Borel isomorphism. Okay, so there's nothing mysterious here. I'm just choosing a set of arrows, if you want, in my equivalence relation that join some source U to some source V, and it induces isomorphism between U and V. Okay, for example, if you pick just one element in G, rho inverse of G, the set of all arrows labeled by G, will be a bisection. Because G induces an isomorphism between X and itself. Okay, I will say that a subrelation S of R is invariant under the bisection if essentially, so if I take, so my bisection goes from U to V. So I want to say that if I take almost every double XY in U times U, so I take 2 points here, So this arrow, so the 2 points are in the subrelation if and only if, when I transport them by the bisection, these 2 points are also in the relation. So X and Y are in S if and only if, after transporting them by the bisection, they are also in S. So here I'm viewing B as a partial isomorphism, so an isomorphism between U and V. So 2 points here are in the sub-relation if and only if their images under the bisection are in S. Okay, and now I'm going to say that S is normalized by R if you can write R as a countable union of bisections such that for every n, S is Bn invariant. Okay, let me give an example. It's probably going to be the only example that I will really use is that if A is a normal subgroup of N, so those are two subgroups of G, then the subrelation coming from restricting the action to A is normal in the subrelation coming from restricted the action to N. So let me explain this example. This will unravel this definitions. Okay, so the thing is, so what do I need to do? I need to write rho G inverse of N as a union of bisections, countable union of bisections. So I will just say N is a countable group. I write it as the union of its elements. So it's the union over N in N, rho G inverse of N. And this is a bisections because it, like the action of little n induces some isomorphism between X and X. There is a unique correspondence between the point in the source and the point in the target. And now, why is this subrelation normal? Because so now you have your bisection where everybody, so in the bisection, all the value of the cocycle is always n. And now I'm saying that an arrow here as its label in A, if and only if, when I transport by the bisection, what is the label that I see here? Well, by the cocycle relation, the label that I see here is N inverse A N. And because A is normal, saying that A is in A is equivalent to saying that A and A inverse is in A. So saying that the label through the cocycle is in A is something that's invariant under the bisection. So I've written this as a countable union of bisections such that when I transport through the bisection, the source is in A if and only if the target is in A. Yes.
for almost every.
Yes, if you. I should say, I think this notion comes from Feldman, Sutherland, and Zimmer. And this example is supposed to suggest to you that this is a natural generalization of the notion of normality of a subgroup. Subgroup is normal if and only if, so you can write N as a countable union of its elements, and every element stabilizes A. And this is a version for equivalence relations. Okay, so now we are ready to repeat the proof of Adam's theorem that I gave at the beginning of the lecture, but phrased in the language of subequivalence relations. Okay, so now recall that I have A, which is my infinite amenable subgroup of H. So I will let A be the sub-relation that's given by just restricting the H action to A. This is a sub-equivalence relation of R. So it comes from the H action, but now somehow I'm going to forget about the H action, just retain that it's a sub-equivalence relation and use the cocycle rho G on A. And likewise, I will let N be rho H inverse of the normalizer of H in A. So we know that A is amenable because A was. N is non-amenable because the normalizer by assumption is non-amenable, and A is normal in N. And now I will use the cocycle rho G. So I view them as a sub-equivalence relation of the one that comes from the G actions. Okay, so since A is amenable, and since G is acting on this compact metrizable space, I know that there is some map from the base space to the space of probability measure on the boundary, which is equivariant now with respect to the cocycle rho G. So this is the same beginning of the proof as before. I said A was an amenable group, and therefore there is an invariant probability measure. Now A is an amenable subrelation, therefore there is an equivariant field of probability measures. And I repeat my two steps. So the first case is when this probability measure, the probability measure I get, has support at least 3. So of course it might depend on the point in X, but let's take as a first case that there exists U of positive measure such that for every X in U, the probability measure mu X has support at least 3. right? So in other words, as before, this says that I have an equivariant map from U to probability measures on the triple boundary. And I can play the same game as before. I push it forward through the important barycenter map. I get a map from U to probability measures on finite subsets of G. And I take the element with maximal measure. And I get a map from U to finite subsets of G. Right here, I'm really just repeating what I did in the group theoretic case. Now, yes. Yeah. So this is G equivariant, right? This is important.
Have a section is think of this as
I don't know. But I see what you mean. But in some sense, I mean, there is, but there is always, for any group, there is always a canonical choice, just because by countability of this. Okay, so I have a map from the base space U to finite subsets. This is a map from a space to a countable set. It takes at most countably many values, of course. And so I can cut U into countably many pieces such that on each piece the map is constant, right? So I can find V inside of U positive measure such that this map is fully theta restricted to V is constant. But now, this is a contradiction. Because, so it's constant and it's also a rho G equivariant. But because you have a set of positive measure, just by Poincaré recurrence, you know that there is some element in A that send a point of V inside V. And this must have some label. This is rho G of the arrow, some label in G. And the equivariance tells that, so if I call, I don't know, theta V, the constant, the equivariance tells me that A theta V should be equal to theta V, but there is no infinite order element of G that fixes a finite set. So this is a contradiction. Okay, so this says that there is no subset of positive measure where the cardinality of the support of the measure can be at least 3. So the measure should everywhere be supported on at most 2 elements. So for almost every x in x, the support of mu x is at most 2. And then I claim that, as in the group theoretic setting, in this case, there exists some unique map nu max from X to subsets of cardinality at most 2, that is a rho G equivariant. Essentially, what do you want to do? You want to take all such maps. You know that there exists one. You take all such maps, and you take the union of all such maps. And it cannot hit cardinality at least 3, because otherwise you would get this contradiction. So nu max is, in a sense, just the union of all A rho equivariant maps from X to subsets of cardinality at most 2. Formally, this is not quite correct, because this would be an uncountable union. And well, to make sure that things stay measurable, you need to only do countable unions. But okay, there is a technical thing here, but it's still true that you can deal with having it. Well, you know, it's only maps that take values at most 2 points. You can deal with only countably many maps. Okay, and now the claim is that by normality, this map is in fact invariant by the normalizer. Okay. And so, why is this? So this is a little exercise in the definition of normality of sub-equivalence relations. It's just that, so say you have some bisection that correspond to the action of an element little n, and you have the map nu max, and maybe on u define nu prime max of x to be, so you have your bisections, here is B of x, and you define it as being something like n inverse of nu max of B of x. You transport the map by the bisection. If you do this, the normality will tell you that you again get some, if you start with any A equivariant map, by doing this, you will still get an A equivariant map on U. And the maximality, this uniqueness, tells you that the map nu prime max has to be equal to nu max of x, which means exactly that nu max of B of x is equal to n nu max of x, which is exactly saying that the map is invariant under the bisection. And because n is a union of bisections, well, it's n invariant, it's n equivariant. So, right, so we are all familiar with it. If A is a normal subgroup in N, and if you have something canonical for A, then it's also N invariant. It's a little exercise in the definition of normality of a sub-equivalence relation to check that in this measurable setting, it's again true that the map is N equivariant. And now we are done, because we have an N equivariant map from X to subsets of cardinality at most 2 of the boundary. But the action here is Borel amenable. And we saw that if you have an equivariant map to something where you have an amenable action, then this forces N to be amenable. This was the second property that I gave about amenable sub-equivalence relation. And this is the desired contradiction. This contradiction concludes the proof of Adam's theorem and shows that H cannot be, so I said orbit equivalent to G, but it's also true in the measure equivalence setting. Okay, so I think I will stop here for today. What I plan to do next time is tell you about some superrigidity phenomena for certain classes of groups where the group, the ME class of a group consists only of the group itself and groups that are virtually isomorphic to itself. And you'll see that really these arguments of Adams will be a crucial step in proving those superrigidity theorems, in the sense that, okay, so I did it for hyperbolic groups, but more generally, if you have a group acting on a hyperbolic space, this will enable us, this kind of argument will enable us to distinguish subrelations that are kind of in the hyperbolic directions from subrelations that have a big normalizer. So typically in a mapping class group, the subrelations, the subgroups with big central normalizers are, if you take a den twist, the normalizer is big. And so this kind of arguments will by looking at the action of the mapping class group on the curve graph, you'll see that we can recognize the subrelations that correspond to stabilizers of curves. And this will be a key step to then say that the equivalence relation encodes the curve complex of the surface, and from this we'll get superrigidity. Okay, so this was just a quick teaser for next time, but thank you.